So now we go on to discuss how this wonderful invention, the reference electrode, is used to set an absolute potential scale by which one can quantify the ease with which metals in this illustration, but molecules in general, can donate or accept electrons, and thereby classify what will be a donor relative to something that will be an acceptor. So let's take a look at this rather complicated setup shown in this picture. What we are going to try and do here is to determine an absolute potential scale for the reduction of metal ions in the solution in this cell over here. So we have here an elemental metal and its corresponding ion in solution over here. And the question we want to address is, what is the potential for this ion to be in equilibrium with this metal electrode? In other words, for a standard concentration of ions in solution, what potential will the Fermi energy of this metal be such that the rate at which metal dissolves into solution, leaving extra electrons behind to raise the potential of this electrode, is exactly balanced by the reverse process of the metal ions in solution being reduced by the electrode to form elemental metal in the electrode. The reference electrode in this case consists of porous platinum onto which is absorbed hydrogen. So hydrogen is bubbled through at atmospheric pressure to absorb on the surface of this porous platinum. So there is molecular hydrogen on the surface of the porous platinum, and it is bathed in a bath of 1 molar acid. So now the molecular hydrogen on the surface of the platinum is held in equilibrium with protons in the acid. The reactions that occur then are the reduction of protons in the acid to form molecular hydrogen on the electrode. That's this reaction shown here. And so when this occurs, electrons leave the electrode to neutralize the ions in solution here. The reverse reaction, in which electrons are donated to the electrode to form ions in solution as the molecular hydrogen becomes oxidized, then raises the potential of this electrode. So finally the Fermi level is held at some equilibrium or fixed potential with respect to the vacuum when these two processes of reduction of hydrogen ions and oxidation of molecular hydrogen are exactly in equilibrium. A key trick is that these two liquid cells are in contact so that any net charging in this cell is balanced by a flow of ions from this cell. So the electrochemical potential in this cell is exactly the same as the electrochemical potential in this cell. This salt bridge is arranged to present a fairly restricted flow of ions, so the chemistry is not seriously altered in this cell by the process of balancing the charge in the two cells. Now, this then means that the hydrogen or the platinum wire reaches its equilibrium potential with respect to the vacuum, and this metal electrode reaches its equilibrium potential with respect to the electrode. So if one now places a high impedance voltmeter between the two electrodes, one that takes essentially no current, so one can measure then the absolute potential difference between the reference electrode and the electrode under test, one can then give an absolute measure of the potential for this metal to be in equilibrium with its ion in some standard concentration of the metal ion in solution on what is called the scale of the standard hydrogen electrode. So by making a series of such measurements, it is possible to quantify the reduction potential for many metals. The result is this table here called the activity series. You can see that a very large potential relative to the reduction of hydrogen is required to reduce lithium. This is because, of course, lithium loves to give up an electron and therefore is very easily oxidized. So conversely, it takes a large potential to reduce it. Running down this series here, you can see that gold is very easily reduced. However, the converse of that is that it is very hard to oxidize gold, which is why it is called a noble metal. These potentials here are listed as reduction potentials. The corresponding oxidation potential, in other words for the reverse reaction, can be found simply by changing the sign of these potentials. So now all of these reactions are quantified relative to the standard hydrogen electrode or normal hydrogen scale, almost equivalent things. And this means then that you can decide what will spontaneously donate an electron to what. So for example, lithium metal would spontaneously donate an electron to any of the metals below it in this activity series. These potentials are all for what is called half-cell reactions, of course, because they are relative to this reaction down here. So how does one measure these things a little more conveniently than the cell I showed you on the previous slide? The answer is by a technique called cyclic voltammetry. This is a technique then that one can apply to solutions, such as solutions of molecules, for example, containing iron in its 2+ oxidation state. And the way this works is that the potential of the electrode is swept relative to a reference electrode, once again the normal hydrogen electrode or standard hydrogen electrode. And what you see is that when you reach the point where there is an equal population of iron 2+ and iron 3+ in solution, these could be ions contained in some molecule, then the current is the highest, because at this point here you have the largest supply of Fe2+, but you haven't completely saturated the solution with Fe3+. The reaction rate falls as you start to saturate the solution with iron 3+, and then when you sweep back again, you see the peak for the reduction, the current increasing now as you start to turn iron 3+ into iron 2+, being a maximum when the two species are exactly in equilibrium. So one can measure these potentials then on some standard reference scale by this process of cyclic voltammetry. A measure of the current flowing into or out of an electrode as a function of its potential with respect to a reference electrode will let us determine the oxidation potential. How do we correct for non-standard concentrations? Well, we know how to do this. This is the famous Nernst equation, which is for volts, what our free energy expression was for joules in chapter 3. We now use the Faraday constant, the charge associated with a mole of material, times the number of electrons involved in the electron, R because we're talking about molar concentrations, and then the famous logarithm of concentration correction to the free energy, where here we have the activities of the oxidized and reduced species, so that we can now correct the standard electrochemical potentials for concentrations that are not standard.